Here's a vector v and two more vectors a and b. A and b are at right angles to each other. They are mutually perpendicular, and A is at an angle theta to v. There's nothing special about the angle theta as drawn. We've drawn it as random as possible to get across the point that what we're about to do is generally true, not just a special case. Now the next thing to notice is that A and B will add together to give v. If we make A and B the right length to form a rectangle whose diagonal is v. You can see that by imagining this rectangle to be a special case of a parallelogram when A and B are at right angles. Or you could reposition B up here and add using the tip-to-tail method. In either case you can see that A plus B equals v. So A and B are two vectors that add together to give v. Another way of saying this is that v can be split up into two vectors A and B that combined together have the same effect. We say that A and B are two components of v. How big are the vectors A and B? Well, their sizes are represented by the lengths of the arrows, and the arrow lengths are linked to the magnitude of v by the sine and cosine of the angle theta. The cosine of theta is the adjacent side, the magnitude of A, over the hypotenuse, the magnitude of v. Notice that we can write the magnitudes using the modulus signs or by unbolding the vectors. Likewise, the sine of theta is the opposite side, the magnitude of b, over the hypotenuse. We can rearrange these two relationships to give expressions for the two components, the magnitude of A and the magnitude of B. A equals v cos theta and B equals v sin theta. It's very important that you can quickly get to these relationships. A way to remember them is that the component that, along with v, encloses the angle is the one with the cosine. Using vector components is always just a means to an end, so if you can find the components mechanically or automatically, then your thinking will be freed up to concentrate on the problem you're really trying to solve. At this stage you could well ask for examples of when resolving vectors into components would be useful. We'll cover that in the next video. You might also ask why the directions we've chosen for the components are any more useful than the one that v is in the first place. And in this general example where we've chosen a random direction, they may well not be. But in specific situations, you'll find that there is a direction to choose that makes life easier, that depends on the situation. We'll look at that question in the next video too. Finally, just a point worth making, we have said that A plus B equals v. Does this mean that v cos theta plus v sin theta equals v? No, it doesn't. Just because the vectors add, it doesn't mean that the magnitudes of their components do. In a way, the components do add, but that way is using Pythagoras. So the square of the magnitude of A added to the square of the magnitude of B gives the square of the magnitude of v. And you'll see here this works out if you know the trigonometric identity that cos squared plus sine squared equals 1.